Hello, my name is Barak Hoffer. I'm a PhD student in the Faculty of Electrical and Computing Engineering at the Technion, and today I will present our work, Stateful Logic in Memory, using gain cell embedded DRAM. So we know that modern applications demand high-density, low-power memory with integrated computation capabilities, and gain cell eDRAM emerges as a promising alternative to SRAM and traditional eDRAM. And this is because this eDRAM offers higher density and lower leakage power compared to SRAM, while retaining compatibility with standard CMOS processes, which is not the case for traditional eDRAM. We have here to the bottom right a typical GC eDRAM bit cell, a 3T bit cell. We have a transistor, a storage transistor, where the storage node at its gate is used to store data. Basically, if this storage node is charged, then this transistor will be conducting, representing a logical 1. And if this storage node is discharged, then this transistor won't be conducting, representing a logical 0. We have another transistor to open the write path to this storage node, where we can charge or discharge the storage node. And another transistor to open the read path to pass current through the storage transistor and sense the stored data inside of the bit cell. There are other flavors of GC eDRAM bit cells. Here we focus on this 3T bit cell, but the same idea can be applied to other types of GC eDRAM bit cells. So I talked about computational capabilities or integrated computational capabilities inside of the memory, and this is to improve the performance of some applications. And here we introduce or we use a concept for that called processing in memory. The idea in processing in memory is we have a CPU and a memory. We know that in traditional von Neumann architecture, that's how computers are built. And we constantly move data from the memory to the CPU and back. And this creates a bottleneck, which hurts the performance of a lot of applications, mostly when we have a lot of data. And to tackle this bottleneck or improve the performance of some applications which are data intensive, we show here the idea of processing in memory, which is basically adding processing capabilities to the memory itself. And in this work, we basically extend the functionality of GC eDRAM by introducing and enabling PIM inside of GC eDRAM arrays through stateful logic, where stateful logic is a method that enables in-memory execution of Boolean logic operations. And since these logic operations are operating locally inside of the array, they can be performed in parallel on multiple data bits across memory rows. And this is our contribution. So how can we implement stateful logic in memory using GC eDRAM? If we look at the standard structure of GC eDRAM array, here we have a single column, which is a single column. We can think about it. One row is multiplying this column to create a row. And here we have an example of 3-bit cells or 3 rows. To write to a bit cell inside of this column or inside of the row, or here a specific bit, we select the write word line, and we charge the storage node of the bit we want to write to, or discharge it using the write bit line. This is how we write. And if we want to read, then we select a read word line, and we can sense the current passing through the read bit line. To add support for stateful logic, we introduce we add basically a transistor per column that connects the write bit line to the read bit line using the logic control signal. And this enables us the implementation of stateful logic operations in memory. How can we achieve that? So we show 2 logic gates. We'll start with a NOT gate. For the NOT gate, we look at a specific bit or a specific row that will represent the input. This will have some data stored inside of it that we want to basically compute the inverse of it. And we have another row that will be used as an output of the logic computation. So after the computation, we have the original data and its inverse of using the NOT gate. And we'll compare it to the NOT gate truth table and see that we get the required output from the operation. So we start with initializing the output to logical 1. Basically, we charge the storage node. And then we perform the logic operation by driving both the logic control signal to conduct for this transistor bit conducting between the write bit line and the read bit line, and also open this transistor of the output by driving the right word line of the output and for that, and the read word line for the input. Now, how will this perform a logic operation? If the input stores logical 0, then this storage node is discharged. So this transistor will be closed, will not be conducting, and there will be no discharge path from the storage node of the output, and it will remain as logical 1, it will remain charged. Opposite to that, if the input is logical 1, then there will be a conducting path from the storage node of the output through the transistor of the input, and the storage node of the output will discharge to 0. And now if we compare that to the truth table, then we see that when we had a 0 at the input, then the path wasn't conducting, so the output will remained at logical 1. And if we had logical 1 at the input, then the path was conducting and the output changed to logical 0. And this gives us, as we wanted, the NOT gate. This idea can be extended to implement a NOR gate. The basic idea is the same. We initialize the output to logical 1. And again, we drive the logic and the line and the right word line of the output and the read word line of the inputs. Here we have basically two inputs. You can see it's the top line, the top row and the bottom row. And now, if both inputs are logical 0, then again, the transistors will not be conducting. So the output storage node will remain at logical 1, it won't be discharged. But if at least one of the inputs is logical 1, then the transistors will be open, will be conducting, and the output storage node will discharge to 0. And now again, if we compare to the truth table of a NOR gate, we see that we got the correct logic operation. Both inputs are 0, then the output won't change and it will remain at logical 1. And if at least one of them is 1, then the output will discharge and we get logical 0 at the output. So this is basically the basic idea we implement here. We implemented, we designed a DC eDRAM bit cell and array. The bit cell we designed is a 3T NMOS bit cell in GlobalFoundries 28 nanometer process. This is the size of the bit cell. We used high voltage threshold transistors for the write access to have lower leakage on the storage node and for that and better performance, and low voltage threshold transistors for the read and storage to gain fast access to the stored data. We selected a array architecture that is built as a hierarchy. Basically, we have 64 by 64 subarrays, and this is multiplied. We used a few times in order to build a larger memory macro, and which for each subarray there are local drivers, and the control is coming as a global control. The area overhead for adding the logic support, the control, and the additional transistor per column is only 0.5%. And again, the idea to have array that is built as a hierarchy, we get another form of parallelism. We have basically we perform a bit operation across rows. That's one form of parallelism. And since we can perform the same operation on multiple subarrays, then we have another form of parallelism where all of those subarrays are performing the logic operation at the same time. We evaluate the performance of the logic operations in simulations. Here we have a node operation, the waveforms for the node operation simulation. We can see here how the operation is performed. First, both the right word line and the logic lines the right word line of the output and the logic line are raised, and this charges the read bit line and the output storage node to an initial value, and then the read word line of the inputs is raised while keeping the right word line and the logic lines high. And this basically opens the read path for the inputs that will change or will not change the storage node of the output. And if we look at the output storage node, the result, then we see that in the case both inputs were storing 0, then the storage node did not change. It remained high. And in the other cases, the storage node discharged and it changed to 0 as we wanted to implement the NOR operation. For robustness and energy results, we show Monte Carlo simulations. For the success rate of the gates, we took 1,000 simulations, and we show that both in the NOT and the NOR gate, we have 99.5% success. We have a specific problematic case which is not 100%, but nonetheless, these are good and robust results. And the data retention time we got is 5 microseconds. For the energy numbers, we show that the operations are energy efficient. For the NOT gate, we have 13.4 femtojoule, and for the NOR gate, we have 13.5 femtojoule. And we say it's efficient since if we compare it to standard memory operations that we also measured in simulation, for read we have 13.3 femtojoule, and for write we have 5.7 femtojoule. And we show that if we wanted to implement these logic functions in a standard memory array, we need to read the data, compute it, and write it back. And we see that we are already better than the sum of these two operations. We didn't even mention here the additional energy required for the computation inside of CPU in standard memory. So we know that our operations are energy efficient, and we can gain from using these operations inside of the memory. To conclude, we showed the design of in-memory logic using stateful logic in GC eDRAM arrays, and we showed that it's robust and showed its principle. For future work, we plan to explore more complex logic operations using these logic gates as building blocks, and we will show how these gates this idea can be applied to suitable computational workloads, and we'll show the performance benefit of using these operations. Thank you.